Good afternoon, dear colleagues. The function is one of the central mathematical objects. Throughout their studies, we introduce students to various classes of functions, from simple to quite complex. And tasks that require understanding the properties of functions constantly appear in the external independent assessment. So what exactly is a function? And do teachers themselves truly understand this important concept? First and foremost, a function is a universal and generalizing term. Function, mapping, transformation, operator, and some other words, all of these are synonyms. However, the term mapping is more often used when one wants to emphasize which sets are the domain and the codomain. The word transformation appears when we talk about functions in geometry. An operator is most commonly used in reference to functions in multidimensional spaces. Such functions may have not just one, but several, or even an infinite number of variables. For example, figuratively speaking, experience can be described as a function of two variables, time and the desire to learn. We know well that a function is an excellent tool for describing complex processes and phenomena that occur around us. Functions can be encountered even in the simplest everyday situations. For example, from birth, information about a baby's weight and height is regularly recorded in their medical chart. But this is nothing other than a tabular representation of two functions. A person's weight and height is a function of age. During our studies, we most often define functions using a single formula. 3x minus 5 times the cosine of x squared minus the cube root of x plus 2. These are the familiar heroes from school. Functions that are defined by different formulas on different sets are less common, and for some reason they are not treated very favorably in lessons. If we recall the history of mathematics, indeed, such functions were not recognized as legitimate for a long time and were refused consideration. In the 18th century, a heated scientific debate arose around this issue. The leading scientists of that time, D'Alembert, Euler, Bernoulli, Lagrange, while discussing the problem of string vibrations, could not agree on what should be called a function. It is believed that this dispute significantly influenced the development of many branches of mathematics. Perhaps it is for this reason that many teachers still consider piecewise defined functions unacceptable. They claim that piecewise defined functions are unnatural from a practical standpoint and never occur in real life. They are seen as artificial mathematical monstrosities. That's a mistake. First of all, these functions have long been completely legitimate and have the same rights as the usual standard ones. By defining functions in this way, we expand our arsenal and add a much larger set of functions to our mathematical toolkit. So why limit ourselves and push away wonderful opportunities? Secondly, piecewise defined functions can also arise in real practical problems. For example, heating ice and turning it into water is conveniently modeled by a piecewise linear function. Exactly, because this process consists of three different stages: heating the ice, melting the ice, and heating the water. Moreover, sometimes it's even impossible to distinguish a function defined by a single formula from one defined by different expressions on different sets. For example, the absolute value function is traditionally defined using a brace, specifying separate values for non-negative and negative arguments. But on the other hand, the same absolute value function can also be written differently using a single formula, as the square root of x squared. Here's another example. The maximum function, which determines the larger of two numbers, is also most often defined using a brace. But again, the same function can be written using a single formula like this. Or, if the absolute value sign still confuses you, like this. By reasoning in a similar way, you can write the minimum function of two numbers as a single formula. In short, there's no need to be afraid of or avoid piecewise defined functions. There are many very interesting entities among them. For example, let's consider the Dirichlet function. When the argument of this function is a rational number, the Dirichlet function equals 1. If the argument is irrational, then the value of the function is 0. Thus, the value of the Dirichlet function, say, at the point 5 is 1, since 5 is a rational number, and at the point square root of 5 it is 0, because the square root of 5 is an irrational number. The Dirichlet function has many remarkable properties. For example, it is periodic and not constant. What's so remarkable about that? You might ask. The sine and cosine functions are also periodic and also not constant. Yes, that's true, but the sine and cosine functions have a fundamental period, namely the number 2 pi. But it is impossible to find the smallest positive period of the Dirichlet function because it does not exist. This means that a non-constant periodic function may not have a fundamental period. How can this be proven? The point is that any rational number is a period of the Dirichlet function, and among positive rational numbers there is no smallest one. Indeed, let's prove that, for example, the rational number 3 is a period of the Dirichlet function. To do this, we need to prove that for any value of x, the value of the Dirichlet function at the points x, x plus 3, and x minus 3 are the same. To confirm this, let's consider two cases. First, x is a rational number, and then x is an irrational number. If x is a rational number, then of course x plus 3 and x minus 3 will also be rational numbers. Because if we add or subtract 3 from a common fraction, we will again get a common fraction. Therefore, in this case, the values of the Dirichlet function at the points x, x plus 3, and x minus 3 are the same and equal to 1. If x is an irrational number, then by adding or subtracting 3 from it, we will again get an irrational number. Thus, in this case as well, all three numbers x plus 3, and x minus 3 are irrational. This means that the values of the Dirichlet function again coincide and are equal to 0. From this, it follows that the Dirichlet function is periodic with a period of 3. Using similar reasoning, it can be shown that any rational number is a period of the Dirichlet function. And thus, we have proven the required property. Moreover, the Dirichlet function is a classic example of a function that is discontinuous at every single point without exception. While doing your homework, you will see this for yourself when you try to plot its graph. Let's consider another example. What do you think? Is there a continuous function that, on a bounded interval, has infinitely many points of maxima and minima? At first glance, it seems impossible, because the function has to rise from a minimum point to a maximum point, and then descend again, and do this an infinite number of times. How could this possibly be done within a bounded interval? Or here's another question. Try to imagine a function that has a strict minimum at 0, but in no neighborhood around 0 is it decreasing to the left of 0 and increasing to the right of 0. Please pause the video and try to find answers to these two questions. It's possible that your attempts were not very successful, and perhaps you even got the impression that such functions do not exist at all. But that's not the case. There is a function that simultaneously satisfies both of the conditions stated. Here's what its graph might look like. A function that defines a curve of this shape can easily be written using a curly bracket. For example, like this. Think about why a curve written in this way has an infinite number of extrema on the interval from -1 to 1, and also satisfies the condition of the second problem. In general, the functions we are familiar with can have incredibly interesting properties, for example, being continuous at only a single point, or being discontinuous at every irrational point and having jumps at every rational one, or taking on all possible real values within any interval, or being continuous but not having a derivative at any point, or having a derivative at every point, but the derivative itself is not continuous. There are quite a few such statements. Many unexpected functions can be found in the wonderful book Counterexamples in Analysis. And did you know, for example, that a numerical sequence is also a function? That's right. The arguments of such a function are natural numbers, and the values are the terms of the sequence in question. For example, the sequence of perfect squares is a table-defined function x squared, defined on the set of natural numbers. In fact, functions surround us everywhere. You may not have thought about it, but such familiar concepts as area, addition, definite integral, probability, and many others are also functions. When doing your homework, I ask you to think about why these mathematical terms are functions, and what serves as their argument. What sets are the domain and the range of these functions? Second task. Write a piecewise defined function as a single formula. In the third task, try to plot the graph of the Dirichlet function. Our marathon is coming to an end. The Contora Pi team sincerely thanks you for your attention. We say goodbye and look forward to seeing you again at future Contora Pi events. That's all for now. Bye! And the learning it's all wrong. Nonsense, right? I used it. A heated discussion broke out. What does Palka mean? Palka. Damn, when I got to that part, I forgot. I couldn't say. They weren't recognized as legal for a long time. They weren't recognized as legal for a long time. They weren't recognized as legal for a long time. It will change. Ooh. And see you again at future Contora Pi events. That's all for now. Bye. Eyes, eyes, eyes. Woohoo. Cut. That's a wrap. Well, cash well. Well, show it.